In the last video, I showed you how we can put an angle into quadrant 1 on the coordinate plane and then show how it has a base of length x, a height of length y, and a hypotenuse of length r for radius. We also redefined or re-represented, I guess, the sine of theta, this is theta down here, as being y over r, the cosine as being x over r, and the tangent as being y over x. And of course, we had representations for the cotangent, secant, and cosecant as well. I'll leave those off for now, partly because I want to save the space, but also because once we know tangent, we know we just need to flip it over to get cotangent, and so on. The nice thing about this representation is that it doesn't matter if your angle is in quadrant 1 or quadrants 2, 3, or 4. Let's take a look at what happens if we're in quadrant 2. Here's an angle in quadrant 2. One way of looking at this top scenario here is that I drew the angle. Let's see, I'll do it this way. I drew the angle. I have my initial ray and my terminal ray, or my initial side and my terminal side. And then I dropped a vertical line down from the, well, if this was a side instead of a ray, I guess I should put a point there instead of an arrow. I dropped a vertical line down from the end of this line segment to the x-axis. And that's what makes it a right triangle. If I do the same thing in this diagram, then I get, I'll do the same thing here though too. I'll erase the arrowhead and I'll just put a point. Makes it a little cleaner. And then I'll drop a vertical line to the x-axis. That's what makes it a right triangle. Now notice that in this scenario, I have x here, the distance from the origin out to where the vertical line meets the x-axis. That's my x distance. My y distance is from the x-axis up to the point, and r is still just the hypotenuse of the right triangle, or the radius of the circle, if you imagine this being on a circle. The same 3 and in fact 6 definitions apply here. I have, let's give this the angle theta. When you're working with these, by the way, theta is always the angle right inside next to, see how it's right next to the origin here. Theta is never this angle up here. It's always the one right down here on near the axis. Okay, so what was I saying? I was saying that as with this diagram, the opposite is y, the adjacent is x, and the hypotenuse is r. Down here, the opposite is y, the adjacent is x, and the hypotenuse is r. So the cosine, for example, of this angle right here is adjacent over hypotenuse, x over r, and that's what we have here. So it doesn't matter which quadrant we're in, any of the 4 quadrants, if I set my angle up and then drop a vertical, I'll get those same 3 relationships, those same 6 relationships, right? Now, something we have to watch out for here is that my x value is negative because I'm not over the positive x-axis anymore. I'm over the negative x-axis. So anytime x is involved, and it's involved in cosine and therefore secant, it's involved in tangent and therefore it's involved in cotangent. Anytime x is involved, the x part of that is going to be negative. So the sine, sorry, getting the right pen, the sine of theta in this case is going to be opposite over hypotenuse, which is y, that's a positive value, over r. The cosine is going to be the adjacent over the hypotenuse. Well, that's x over r, but it's negative, right? So if I write this like this, then I'm saying the x value is the numerical value, the absolute value, but it has to be negative. It's still, in practice, it's still x over r, but x is going to be a negative number. So actually, it would probably be more accurate for me to write it this way. If I say cosine is x over r, and it will be less than 0. Sine is y over r, and it will be greater or equal to 0. Okay, and tangent will be, tangent is opposite, which is positive, over adjacent, which is negative. Tangent is y over x, but it's positive divided by negative, so that will also be less than or equal to 0. So in quadrant 2, the sine of an angle is positive. The cosine and the tangent are negative. Because the tangent is negative, the cotangent is also negative. Because the cosine is negative, the secant is also negative. Because the sine is positive, the cosecant will also be positive. All right, let's take a look at an example. And then once I've done that, I'm going to do one for each quadrant so we can see exactly what happens in each case. I'm going to start by finding the sine, cosine, and tangent of 2 pi over 3. To do that, I'm going to start by looking at where 2 pi over 3 is. What is that angle? Well, let's see, 2 pi over 3 in terms of degrees, my pi's cancel, 3 goes into 180 60 times, so I should not have canceled my degree symbol there. My pi's, my radians canceled, my degrees do not. 2 times 60, which is 120 degrees. But I can use that idea, 2 times 60, to figure out where this angle is. If this is 30, 45, and 60, then this is 60 degrees. That's not very accurate, but it'll do. And I want 2 of those. So I'm 60, a second one of those puts me over here. And actually, it puts me at 90 plus 30. So this angle right here is 30 degrees. But since 30 plus 60 is what is equal to 90, this right here is also 60 degrees, or pi over 3. So conveniently, the 2 pi over 3 angle, which is this side of it right here, let me get the right pen, this is 2 pi over 3. 2 pi over 3 has what we call a reference angle of pi over 3. Maybe yellow would have been a better color. Not doing a very good job there. My angle that I'm interested in is 2 pi over 3, which is 120 degrees. Its reference angle is pi over 3, or 60 degrees. So now I'm going to do what I did over here. I'm going to drop a vertical line. I'll tidy this up in just a second. That makes a right angle here, which makes this a right triangle. And let's take a look at that triangle. Let me clean this up and we'll take a look at that triangle. All right, here's my angle 2 pi over 3. Here is my vertical line down to the x-axis, always to the x-axis. That's what creates a right triangle. And that's also then what creates this reference triangle, which is pi over 3 here. And that automatically means that this angle is pi over 6, but I don't care about that. Pi over 3 is 60. Pi over 6 is 30. So 60, 30, 90 triangle, or 30, 60, 90 triangle. I don't care about this one right now. All I care about is this one, because this is the one that's the reference angle for 2 pi over 3. Let me put that in as well. 2 pi over 3 is the one whose sine and cosine I want. But I'm going to use the fact that the height above the x-axis is the same here as it would be over here. And the distance out from the y-axis is the same as it would be if I were dealing with the pi over 3 angle, right? So what is, then the question becomes, what is the sine, not of 2 pi over 3, but of pi over 3? We know that from our chart. The sine of 2 pi over 3 is the same as the sine of pi over 3. The cosine of 2 pi over 3 is the same as the cosine of pi over 3. And the tangent of 2 pi over 3 is the same as the tangent of pi over 3, with the possible exception of the sign, S-I-G-N, plus or minus. And that's what we need to figure out now. Let's take a look at, I'll use a pen here and I'll label green for positive and bright pink for negative. I've been told that pink and green, as much red as there is in pink, pink and green is not too much of a problem for people with red-green color blindness. If that's not true, please let me know so I can stop doing that. I'm only using pink and green because those seem to be the right colors for positive and negative in this environment. I don't have red, and I wouldn't want to use red and green anyway. Okay, so I'm going to label the side of the triangle that is positive with green, and that's the hypotenuse, which will always be positive, and the vertical side, because it's above the above the x-axis, it's positive, but the The horizontal side is it's lying on the negative x-axis, so that has a negative value. So now when I go back in and find my opposites, hypotenuses, and adjacents and whatnot for my sine, cosine, and tangent, I'm going to get the same value as I would for sine, cosine, and tangent of pi over 3 instead of 2 pi over 3, but the sign may be different, SIGN, plus or minus. So let's take a look. For the sine of 2 pi over 3, I need to know what the value is for the sine of pi over 3, and that is whatever the value is going to be. It's going to be opposite over hypotenuse. Well, that's opposite, which is positive, over hypotenuse, which is positive. So that one will be positive. The cosine will be adjacent, which is negative, over hypotenuse, which is positive. Negative divided by positive is negative. The tangent will be opposite, which is green, positive, over adjacent, which is red, negative. Positive divided by negative is a negative. So the statement that I made earlier, that the cosine of 2 pi over 3 was the same as the cosine of pi over 3, was only partially true. The numerical part of it will be the same. This part and this part will have the same numerical value, but because the angle 2 pi over 3 is in quadrant 2, it will be negative. The value will be negative. Okay, now we can figure out what those values are. We know from our chart that the sine of pi over 3 is the square root of 3 over 2. I'm moving things around as I go here because I didn't really have room otherwise. Square root of 3 over 2. And it's going to be positive because we decided that in quadrant 2, sine was positive. The cosine of pi over 3 is a half, but the cosine of pi over 3 for an angle in quadrant 2, because cosine is adjacent over hypotenuse, it's always going to be negative. And the tangent is always going to be negative as well, because tangent is always opposite over adjacent. And in quadrant 2, opposite will always be positive and adjacent will always be negative. So it's going to be a negative value, and that value is the square root of 3. Now, I've mentioned this a couple of times, but I've sort of done it on the fly, and I'm going to make it a little bit more formal by saying it again here. I have done this exercise for one angle, 2 pi over 3. I have found the sine, cosine, and tangent of 2 pi over 3. That angle happens to be in quadrant 2. But it doesn't matter where in quadrant 2. Let me draw another angle just very quickly here. Here's another angle in quadrant 2, which if I drop a vertical for that one, I get opposite, which is going to be positive. My adjacent will be negative because it's on the negative x-axis, and the hypotenuse will always be positive. So it doesn't matter where in quadrant 2 we're sitting, the sine will be positive, the cosine and the tangent will be negative, no matter what the angle is. So there are actually two skills involved with finding the sine, cosine, tangent, cotangent, secant, or cosecant of an angle if that angle is not in quadrant 1. One is finding out where the angle is and identifying the quadrant that it's in, and the other is recognizing the reference angle for it and finding the sine, cosine, or whatever of that reference angle, and then applying the correct sign, SIGN sign. So let's take a look now at a couple more examples. Okay, I've drawn this coordinate system here, and I've put generic angles in quadrants 1, 2, 3, and 4. When I drop a vertical for any of those angles, I get this one here, there's one there. Dropping a vertical is a bit of a misnomer here. I guess you could drop it in the other direction, I suppose. Same thing here. And in each case, that is how I end up with a right angle. There's a right angle here, a right angle here, here, and here. Notice that I always drop the vertical, and it's a vertical, so it's going to the x-axis. A lot of times I'll see students take an angle and then try to draw a horizontal and make their right triangle that way. It doesn't work. That does not work. Because you're getting which angle do you use? Do you use this one? In which case, what's your opposite? Well, it's the same as this, but it's not part of the same triangle. So just don't do it that way. It's very very clear that the way to do this is to drop a vertical down to the x-axis. You want to meet the x-axis here, okay? So now that I have those, I'm going to relabel them. Got an errant green line there. Everywhere that there's a positive y value, I'll use a green line. And everywhere there's a positive x value, or positive x side, I guess you could call it. I'll use a green line there as well. Let's see. Wherever there's a negative y, right, I'm going down below the x-axis here, so those y's will be negative, and negative x will occur there and there. And of course, my hypotenuse will always be positive, so I'm just going to leave those for now. All right, let's talk about sine. I should label my angle theta. Theta will always be this angle in that case, this angle, right, the one closest to the x-axis. For quadrant 1, sine, well, always sine is opposite over hypotenuse, but in quadrant 1, sine is positive. I'm going to do that for all 4 quadrants. For quadrant 2, I have opposite, which is positive, over hypotenuse, which is also positive. In quadrant 3, I have opposite, which now it's negative, right? This is a y value. If you plotted this point right here, you'd have a negative y value. So you'd have a negative x, negative y. But all I'm interested in is the length of the side here is whatever y is, but it's below the x-axis, so it's going to be negative. Sine is opposite, which is negative, over hypotenuse, which is positive. So negative divided by positive is negative. And in quadrant 4, again, I have opposite, which is negative, over hypotenuse, which is positive. So it's negative there. All right, now let's do the same thing for this software. Will let me move things off screen, but then it doesn't stick. It's very annoying. So I have to go back in and move them while I'm recording. I find that really rather annoying. Okay, let's do the same thing for cosine. Cosine is adjacent over hypotenuse. In quadrant 1, we have adjacent, which is positive, over hypotenuse, which is also positive. So in quadrant 1, the cosine is positive. In quadrant 2, we have adjacent, right? This is my angle here. My adjacent side is this one here, so it's negative. A negative over the hypotenuse, which is positive. So cosine is negative in quadrant 2. In quadrant 3, I have negative, a negative adjacent, and now I'm adjacent to this angle, negative adjacent side over the hypotenuse, which is negative. Cosine is negative in quadrant 3. And in quadrant 4, I have adjacent, which is positive, over hypotenuse, which is also positive. Remember, the hypotenuse is always positive. Now we'll look at tangent. In quadrant 1, I have opposite over adjacent, both are positive. In quadrant 2, I have opposite over adjacent, which is positive over negative, so that's negative. In quadrant 3, I have opposite over adjacent, negative over negative, which is positive. And then in quadrant 4, I have opposite over adjacent, which is negative over positive, which is negative. So now I know what the sine, cosine, and tangents are the signs, SIGNs, for sine, cosine, and tangent for all 4 quadrants. And because I know the sine, SIGN, for sine in quadrant 2, I also know the sine, SIGN, for cosecant. Because I know the sine, SIGN, for tangent in quadrant 3, I also know the sine, SIGN, for cotangent. And because I know the sine, SIGN, for cosine in quadrant 4, I also know its sine, SIGN, for secant. So I don't need all 6. I only need the 3 primary ones, which is why I call them the primary functions, right? At the very beginning of the course, I talked about these being the 3 primary functions, and the other 3 are just as valid, but we don't necessarily need them because all we do is flip cosine and we get secant. So now I know the signs, plus or minus SIGN, for all 6 functions in all 4 quadrants. There are several different ways you might consider trying to memorize these signs, but one way that I think a lot of people find useful or helpful is to just remember which ones are positive where. And except for the first quadrant, notice that you have one function that's positive in each of the four quadrants, each of the other three quadrants, 2, 3, and 4. Here, everything is positive. So let's call that all. In quadrant 2, only the sine is positive. Everything else is negative. Sine and cosecant, right? If sine is positive, so is cosecant. In quadrant 3, it's only tangent that's positive. And in quadrant 4, it's cosine. And a lot of people I know, including your textbook, use these four letters, and the fact that we always go, starting in quadrant 1, we always count the quadrants counterclockwise. We count, this is quadrant 1, this is quadrant 2, here's quadrant 3, and this is quadrant 4. We always count in that direction. If you do A, S, T, C, you get all students take calculus. That's just a mnemonic. It's just a memory aid. You can do whatever you want, make up a different expression if it will make more sense to you. There's no rule that says you have to use my memory aid. The idea of a memory aid is to help you remember. All students take calculus is just about as ubiquitous as SOHCAHTOA. Remember that one? SOHTOA. So, oh, I got it wrong. See, I never use this, so I don't have it memorized. Hypotenuse, TOA, which stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. That's a memory aid. If it works for you, great. If it doesn't, find something else. And that's the same. That same can be said about this memory aid here. All right, I do use this when all students take calculus. That's just how I remember where the positive functions are. All right, so let's do a couple of examples. We'll start with this one. Find the tangent of 5 pi over 4. Remember, there are two parts to this. One is figuring out where that angle is and what the sine is going to be for tangent, and the other is getting the right numerical value. So let's start with figuring out where the angle is. I explained the way I think of these. If I have pi over 4 in the first quadrant as being 45 degrees, and that's just something you'll get used to over time. Another way to think of it is, if you remember that this is pi, then pi over 4 is 1/4 of pi. There's pi over 4, 2 pi over 4, or pi over 2, 3 pi over 4, 4 pi over 4, or pi, and then 5 pi over 4. So I have 1, 2, 3, 4, 5 pi over 4s. That's how I think of these. So the angle that I'm interested in is this one here, 5 pi over 4. But to find the numerical value for that, I'm going to drop a vertical, creating a right triangle. There's my right corner, my right angle corner. And then I'm going to use this triangle to do the work, and then go back and figure out what the sine is, the sine SIGN. By doing the work, I mean figuring out how can I put theta in there so you can see it. I'll do it with a different color. Let's try that. Now that's really kind of hard to see still. But theta is right in here. I've drawn it in there, but it's hard to see. But this is the angle theta. And tangent is opposite over adjacent. So I have opposite over adjacent, which is going to be negative because it's down here. And adjacent, that's negative as well. And so my value is going to be negative over negative, which is positive. Positive. But it's going to be positive the same as the tangent of the reference angle. And the reference angle is just this little angle here, not the big one that we were actually looking for the value for, but the little reference angle, the one that makes our right triangle, right? That's just pi over 4. So the tangent of pi over 4 will tell us what the tangent of 5 pi over 4 is. And because it's in quadrant 3, we know it's positive. That's because it's opposite over adjacent, and they're both negative. But also, you can use, where am I? You can use this idea down here. We're in quadrant 3, so tangent will be positive. Let's put one of these down here as well. All students take calculus. Tangent is positive in quadrant 3. Now, that tells us that my final answer will be positive whatever the tangent of pi over 4 is. And the tangent of pi over 4 is 1. So my answer is 1. The tangent of 5 pi over 4 is positive 1. All right, let's do another one. Find the cosine of 5 pi over 6. One of the two things I need to do is figure out where that angle is, and once I know what quadrant it's in, decide whether its cosine is going to be positive or negative. So pi over 6 is 30 degrees. That's a little too big. 30 degrees looks something like that. There's pi over 6. There's 2 pi over 6, or pi over 3. I'm just doing a little bit of algebra. 2 pi over 6's is 2 pi over 6. When you reduce that, you get pi over 3. That happens to be 60 degrees. If I go another one, I get 3 pi over 6, which is right here on the y-axis. 3 pi over 6, if you reduce that, you get pi over 2. That happens to be 90 degrees. Okay, then 4 pi over 6. So I'm just adding pi over 6, another pi over 6, another pi over 6. That's 3 of them. Here's 4 pi over 6. I need one more. 5 pi over 6. Now I'm going to erase my scratch work here, my demonstration. 5 pi over 6 is this angle right here. This great big angle right here. That's 5 pi over 6. That is actually the angle whose cosine I want. But I'm going to use this triangle, this reference angle, this reference triangle to find it. Okay? Now, figuring out if this is 5 pi over 6, what is this angle here? What is theta? What is my little angle right here? Well, you can do that by converting it to degrees and then subtracting from 100, 180. Or you can just think, well, this is 5 pi over 6's, and this is pi. That must be 6 pi over 6's. So that leaves, down here, 1 pi over 6. This angle right here is pi over 6. That's 30 degrees. Okay, so I'm going to actually find the cosine of 5 pi over 6 by finding the cosine of pi over 6. I've got my pi there is kind of in the way, so let me move that. Okay, so I'm going to find the cosine of 5 pi over 6 by finding the cosine of pi over 6. That's my reference angle for 5 pi over 6. And then I'll go back and figure out what the sine is. Well, I know that the cosine of pi over 6 is the same as the cosine of 30 degrees, and that's the square root of 3 over 2. Now all I have to do is figure out whether it's positive or negative. In this case, I'm in quadrant 2. Quadrant 2. Quadrant 2. Only sine is positive in quadrant 2. Cosine and tangent are both negative. So that means my cosine here is going to be negative. And that's my answer. The cosine of 5 pi over 6 is equal to negative, I should erase that one, erase the plus here, is equal to negative the cosine of 1 pi over 6. So it's equal to negative the square root of 3 over 2. One more. Let's find the cosecant of 5 pi over 3. Now we haven't done one yet that wasn't just a sine, cosine, or tangent. This one is a cosecant, so that's 1 over the sine of 5 pi over 3. But this is a really good way to show you what that really means. The cosecant of 5 pi over 3 is equal to 1 over the sine of 5 pi over 3. So once I find the sine of 5 pi over 3, I just take its reciprocal. All right, let's figure out where 5 pi over 3 is. Pi over 3 is 60 degrees. That's about, maybe I will just do it with my pointer. That's about here. That's 1 pi over 3, 60 degrees, right? You have 30, 60, 90. 60 degrees is 2/3 of the way. A second one of those is about here. That's 2 pi over 3. 3 pi over 3 is just pi, so now I'm here. 4 pi over 3 is another 60 degrees, and 5 pi over 3 is one more, so I'm down here, right about there. So the angle I'm actually finding the cosecant for is this great big angle right here. But the angle I'm going to use to do the work is this angle right here, right? I'm going to drop my vertical. That makes a right triangle. And then I'm going to ask myself, what is that angle? What is that angle right there? Well, this was 3 pi over 3, 4 pi over 3, 5 pi over 3, right? So this was, what's left is 1 pi over 3. 5 pi over 3 to 6 pi over 3 is pi over 3. This angle right here is pi over 3. Now, I think I said that that was 1, 2, 3, 4, 5 pi over 3. So how do I get to 6 pi over 3? What is 6 pi over 3? 6 pi over 3 is 2 pi. 6 pi over 3 is 2 pi. In other words, how do I get from here back up to where I started, right? If that's 2 pi, where did I stop? I stopped at 5 pi over 3, 1 pi over 3 short of 2 pi. Okay, so that's how I knew that this was pi over 3, that the reference angle was pi over 3. So to find the cosecant of 5 pi over 3, I need to find the sine of 5 pi over 3, and that's going to be equal to the sine of 1 pi over 3, but with a plus or a minus. And now I have to go figure out what the plus or the minus is going to be. I'm in quadrant 4, and in quadrant 4, cosine is positive, but that's it. Sine is not positive. That means that in quadrant 4, sine is negative. So I can erase my plus, and I'm left with negative 1 over the sine of pi over 3. That's negative 1 over, looking at my chart, I can see that the sine of pi over 3 is the square root of 3 over 2. 1 over the square root of 3 over 2 is 2 over the square root of 3. So my answer is negative 2 over root 3. The cosecant of 5 pi over 3 is 1 over the sine of 5 pi over 3. And that's the same as 1 over the sine of 1 pi over 3, but it's negative because I'm in quadrant 4, and cosine is the only thing that's positive there. Sine is negative in quadrant 4. So negative the sine of the reference angle. I know what the sine of pi over 3 is. I have that in my table. And then once I have this, I just need to invert it, right, to find its reciprocal. All right, a quick note on notation. Your textbook uses theta for the angle. For the reference angle, they use theta with a bar over it. I've also seen theta with a little tick mark next to it. I would read that theta prime. I would read this one as theta prime and this one as theta bar. And what they're indicating here is that this angle is really my theta. That's the one I'm really interested in. What this one is here is somehow kind of related, not kind of, somehow related to theta, but let's give it a different name because it's not the same size as theta. So that's the way they are representing these angles. Is the reference angle is called theta bar, and that's a little bit different from the way that I've worked through these problems. I'm just calling my reference angle theta in each case, but I know in my head that the angle I'm interested in is this big angle here, and that theta is just my reference angle. Where's the other one? This big angle here is my real angle of interest, and that theta is just a convenient label, right? So again, it doesn't matter how you label these things, as long as you're clear and consistent. I've done it this way. Your textbook uses a slightly different name for the reference angle. That's fine. They're consistent in their use of that. Use whichever of those is convenient and makes sense to you. The one other thing that I would point out here is that I've done all of my examples in radians, but the same thing applies in degrees. For example, this one here could very well have been written as find the tangent of, I have to think about this now, it's 180 plus 45 is 200 and, I'll have to do it, 180 plus 45 is 225. So find the tangent of 225 degrees, right? I could have written it that way instead. Then I would have said, well, that's 180 degrees. So what's my reference angle? It's whatever this number is minus the 180 degrees. That's going to give me 45 degrees, right? But I'm still in quadrant 3, where tangent is positive. All students take calculus. All students take calculus. Quadrant 3, tangent is positive. So I'm going to have a positive tangent of 45 degrees, and the tangent of 45 degrees is still 1, because 45 degrees is just a different name for pi over 4. Okay, in this video, what we've been looking at is how to find the trigonometric value, or the trigonometric ratio, for any angle, even if it's bigger than 90 degrees. If you stick to a right triangle, the biggest angle you can have in there is a 90-degree angle. And we don't even know how to find the sine, cosine, or tangent for 90 degrees yet. We'll get to that eventually. But we've been stuck so far finding the sine, cosine, and tangent for angles between 0 and 90 because we've restricted ourselves to working within the confines of a right triangle. But it turns out we can take that right triangle and put it into a bigger setting, like this one here. This is still a right triangle, but notice that the angle I'm getting here is bigger than 90 degrees. So we've extended what we know about right triangle trigonometry into a larger environment. We're still using right triangle trigonometry, and basically the only thing that's changed is that the reference triangle is our right triangle. Sines, cosines, and tangents have the same values as they would if this was a right triangle free floating in space. But because we're in the quadrant system here, we can now also assign signs, S-I-G-N, pluses and minuses, to how far out or down or up or across we go in the X and Y direction. In the next video, we're going to be looking at something called identities. Well, we've already addressed this a little bit. I've given you some examples and told you these things are called identities, but we're going to formalize that in the next video. We're going to review some that we already know, and there are quite a few of them. And we're going to look at a few new ones. We'll also take a look at a couple of examples of how to use them.